Okay.
Hello, everyone. My name is Qiugang Zong. I come from Peking University. And this morning, Professor Zong just told me to take his place to give a talk. So I just made this talk in this morning. So, as a technical PI of this instrument, so my talk is more technical. So I will introduce the initial results of our instrument, energetic electron spectrometer (EES) on board Macau Scientific Satellite 1. This is our team. It's PI, Professor Zong. It's me. This is the technician, Dr. Ye, and this doctor is for data analysis. So. Which one? Okay, just three parts. First one is introduction, initial, and the conclusion. So this one, Professor John just introduced you the scientific objects of these satellites. But my focus just for the EES. And the first one is we just focus on the generation and the loss mechanism of the inner belt electrons. Actually, the instrument on board the MSS-1 just can measure the inner belt electrons. The second is we want to do some crazy 3D SAA structure study, just because the two satellites in the future will have different orbits. Now they are in the same orbit, just like elliptical orbit, 460 times 500 km. But in the future, the A satellites will change to circular orbits, like at 450 kilometers. So maybe we'll have a crazy 3D measurement in SAA. This is our installation of the instrument. This one, okay, I will. This part is for the ES on board A satellite. They have two parts. One is for the mid-energy electron spectrometer, and other one is this is a high-energy electron spectrometer. For satellite B, we just have the mid-energy electron spectrometer. But you can see this one just have a special structure. The reason is that to avoid the solar cell panel, we have to turn a little bit, just 7 degrees to keep our view angle. Okay. This is a parameter comparison with other similar instruments. We just compare with point MEPD and Demeter IDP. So from the energy range is almost the same, but our energy resolution is a little bit higher than them. We have in orbit multi-channel mode, so we get 128 energy channels, and our energy resolution is about 5 keV. So we can see the result. You can see the difference. The sampling rate is 1 second for it's almost equal. But our best character is angular resolution. We have 18 directions into satellites. So comparison the points, I think we know they just have two directions. One is for 0 point pitch angle, and another is 90 degree pitch angle. But for Demeter, they just have one telescope, so it's our best point. Let's show the initial result. The first is the milestone. We just okay, this one is not so simple. We just pass it. Okay, I will show our result. The first one I show is the physical distribution. It's from 90 to 130 keV electron flux measured by the MES. So we can it's accelerated in 3 months. So we can see very clear that we can just scan the inner yes, it's inner belt in the high latitude region and the SAA. So it's these two panels just show the flux in different MLT. The left one is night side. The right one is this side. They have a little bit difference, but I have to point it out. Here, and this one. This one is not so easy to see, but it's important because it's the electron precipitated by the NWC. So we can see the difference. It's I will say it in the letter. It's for the B satellite. Okay, it's almost the same. Let's make the comparison with Demeter RDP observations. As the inclination of the Demeter is a little bit higher than MSS, so they have better coverage of this the flux maps. But if we just focus on our MSS coverage, almost the same. So that means we have to, in accord with measurements of Demeter. This one is MES countries in multi-channel mode, so we can see very refined distributions in the different energy channels. Of course, it's a count rate, but I will show you if they change it to the flux, they can see it's quite clear. This for the high energy spectrometers. So here you can see we have some little bit proton contamination that the spikes. So you can see, but besides, we can see there's no more proton contaminations. This B satellite observation. Okay. Okay, we can compare the energy spectrum of the mid-energy electron spectrum and compare with the radiation belt models, just like A8 or A9. So here we can see the black lines show the MED measurement in for A satellites, and the blue line is A9 spectrum, and the red line is A8 mean spectrum. So generally the MES A spectrum is in accord with the radiation belt models. It's average the spectrum at SA center. So, and besides, we also can see the energy range of our instrument. We can see the nominal parameter is 50 to 600, but actually we can measure 40 to 700 kV. It's better. Its speed is almost the same. Okay, it's in the same time interval and the same place, the ICA center. The spectrum measured by mid-energy spectrum in onboard A and B satellite. So they almost the same. So that means it's very equal. That means we can use these two instruments measurements to study the same phenomenon. This energy spectrum is for high energy and electron spectrometer. So our nominal energy range is 0.5 to 2 MeV. Actually, we can see the energy spectrum from 200 to almost 3 MeV is also the same. It's very good, and it can be compared with that for AE9, and especially for the spectrums lower than 1 MeV. But you can see for the higher part of the spectrum, the higher that fluctuations, I think it should be maybe caused by the proton a little bit proton contaminations. Oh, okay. Our best character is pitch angle measurement. So this one is just for the MES in A satellite, the pitch angle distribution of the 6 different mid-energy electrons. So you can see, we can see each one, we have the peak in near the 90 degrees. So it's just following the expected results. It just show our performance is good. This one is speed, but we can say the pitch angle coverage is different. So if we just put them together, we can see the pitch angle for these two satellites very close. So that means if we have these two satellites observations, we have very good coverage of the pitch angle distribution and very high pitch angle resolutions. Okay, another one is NWC effect. As we know, there is a ground VRF radio station, NWC, near the west coast of Australia. And then this one, the left, this one is just a diameter observation for this wave. So they just Rosenberg just presented that the man-made VRF waves might have effects on the energy particles in the inner radiation belt, but seldom observations are found. Until recent years, this one is measurements from POIS MEPD. It's a ratio of the 100 keV electron flux measured by as NWC switch on and off. So we can say if they switch on, the flux will be increased. And Dimitri also find this sweep structure. This is separate the electrons precipitated by the NWC waves. We also see these structures, but with more high resolutions. The left one is for A satellite measurement, and this one is for B satellite measurement. So if we just say this WISP-Dirac distribution of the WISP structure, we can see we just distribute in this for arrow just point in the place. So it's the same like Dimitri measurement. Okay, it's B. Okay, that's fine. Okay, thank you.